Hello everyone, this is Rugamba Gloria and I'm going to take you through machine learning. So machine learning is a subset of artificial intelligence that enables systems to autonomously learn, improve and make decisions from data without being explicitly programmed. We have two types of machine learning. We have supervised and unsupervised. Supervised is where we are going to use specific labeled data to help us in future instances. For example, weather forecasting. Let's say we're going to use past historical records. Let's say for a day to be declared a sunny day, it has to have a certain temperature between a certain temperature interval. Then if a day is said to be cold, then it has to have also a certain temperature interval. So that means we are using already data. So we are going to use data to predict future instances in supervised. Then we have unsupervised, where there is no target attribute. We just need to explore that data to find intrinsic structures. So another thing we shall look at is handling unlabeled data sets using algorithms such as clustering, which is grouping together the features, and then anomaly detection, where we have an unusual occurrence of a data instance in a data set, then hierarchical clustering. Then we have the machine learning pipeline, which is like the processes taken in machine learning. Feature scaling, which is a pre-processing step where we feed data into the machine learning. Within feature scaling, we're able to tell whether the model will perform well or not. And in this case, we are going to use two ways, either normalizing the data or standardizing the data. And then we have min-max scaling, then standard scaler. Yeah. Then in data cleaning, here we are basically cleaning the data that's within our data set. And in this case, we are trying to make it improve on the accuracy of the model we are trying to build. So we do this in various ways that are stated below, as you can see. Then we have key terms here. Linear regression, which is a form of supervised machine learning algorithm that's used when the target value is numerical. Then we have another checkpoint, which is every machine learning model should have three things. That is a prediction model, cost function, and an optimizer. Cost function is where we compare the predicted with actual value. Then the optimizer is where learning takes place within the machine learning model. So we have two things here, clustering and classification. And here we are able to see that clustering is an unsupervised technique, while classification is a supervised technique. So for classification, we are using labeled data to assign items to predefined categories. While in clustering, we are analyzing unlabeled data to find natural groupings based on similarities. So that's the key difference between the two. And then the examples of clustering, there is centroid-based, density-based. Then for classification, we have logistic regression and naive-based classifier. So within machine learning, we use different kinds of models. That's the MathStats model, which also involves other models such as deterministic models, probabilistic models. Each of these has their different characters, as you see on the screen for the deterministic. And then here we have the probabilistic models. And the types of probabilistic models are regression and correlation. Now for the regression models, these are supervised learning algorithms used to predict continuous numerical values. Unlike for classification, regression predicts quantities such as, let's say, price, temperature, income. Yeah, for example, predicting house price based on the size and location, predicting student marks based on study hours. Yeah. Then we have the parametric and non-parametric models. And we can see that for parametric, we have a fixed structure and use predetermined number of parameters to capture relationships. For example, we have the linear regression and logistic regression. Then for one other thing about the parametric models, they excel with smaller data sets and they offer computational efficiency. Then for the non-parametric, in these models, we make few assumptions about the data distribution, allowing the number of the parameters to grow with the training data. Then we have another term, cross-validation. So what is this? This is grouping data into key groups. We're going to use one part of the data. Let's say if your K represents 5 groups, you've split your data set into 5 groups. You're going to use 3 of these groups to train, then the other 2 for testing. So another technique under cross-validation is the K-fold, which is just a resampling technique that assesses a machine learning mode's performance by dividing that data set into K equal-sized folds and iteratively training or testing across them. Key benefits: it maximizes data use by training on most samples each iteration. Yeah, then we have the common variants, which are the stratified, repeated. Then we have KNN, which is also an algorithm applied in machine learning. More specifically, that is the classification and regression tasks. Yeah, as you can see, it relies on pairwise distance between the points. It's basically helps us to see the much differences within the different kind of data we are dealing with. Yeah, and KNN use cases include text mining, finance, and Google competitions. Every feature is weighted equally in finding the nearest neighbor. So if all features are equally important, but they are not on the same scale, then they must be first normalized. So here we have the pros and the cons. Yeah. Then we have Gini impurity and Gini index. These are terms that are found that rely on iris data sets. And for Gini impurity, it's measuring a data set's purity. That is quantifying the probability of misclassifying a random sample. Then for Gini index, it's like a weighted impurity reduction from splitting a node. Yeah, and the iris dataset features 4 key attributes. That's the sepal length, sepal width, petal length, petal width. Then we have another algorithm, which is the random forest. It's an example of an ensemble machine learning. Ensemble machine learning, it combines multiple models to produce more accurate predictions than any single model alone. And the techniques used in random forests are bugging, which is training models on random data subsets in parallel. Boosting, here it's done sequentially. Stacking, you're using a meta model to blend outputs from base models. Random forest, it is less interpretable than single trees and can be memory intensive with many trees. Then we also have decision trees in machine learning, which are a supervised machine learning algorithm. And they are a form of a tree-like structure that start with a root node representing the full data set. moves to the internal nodes as feature-based splits, then branches as outcomes, and the leaf nodes as the final predictions. Yeah. So from what I have learned, we can use machine learning to build models that can predict, let's say, for example, weather of a day. Yeah, let's say if my project, I want to determine the weather of the coming days ahead, I'll use data of previous days that are going to enable me to acquire interval ranges that I'll use that will then be used to determine the future weather forecasts of the coming days. Yes. And also it can also be used for disease detection. Yeah. Thank you so much. This is what I had to share. Thank you for listening.